This lecture is about Experiment 10, Molar Volume Lab. I'm going to walk you through the calculations and see if we can get to the end together. So please take out your lab. I'll wait for you. Okay, I'm done waiting. You take out your lab, give me a little pause, and I'll continue. Okay, so you have some data that I don't have, and I'm just going to make up some data that probably won't work out, but you can go work right along with me. The reason that I've changed my plans a little bit about working with this lab is because, well, very simply, I know the take-home quiz due tomorrow is based on a lot of these principles. And I want to make sure that you clearly understand what's going on in a take-home lab. And by working through these calculations, I think you can see that. So I'm going to assume my mass is 0. Let's get rid of that. All right, again, I'm making up my numbers. So I'm going to get 0. I don't know, 0.067 grams. All right, volume of H2 and water gas collected. I'm predicting that we measured from the eudiometer tube, okay, written, and it should be 2 decimal places. It's a very precise piece of equipment. That we get, I don't know, 60, no, I want to say 45.03 milliliters. Okay, barometric pressure today was, let's produce it, was 764. Okay, I'll just keep it at that, and I'll keep that torr, which is millimeters of mercury. Notice in class, what did I give you? I gave you, I believe, 30.09 inches of mercury, and you guys had to convert that. Okay, now of course you should know that 2.54 centimeters, if you're true geeks like me, is equivalent to, I'm sorry, I guess I'm not that much of a geek. 2.54 centimeters, yes, is in 1 inch. All right. So you should be able to convert that to centimeters or directly into millimeters. If it's millimeters, it's 25.54 millimeters equal to 1 inch, and you should be able to convert that. Okay. Temperature of the water bath, let's just make that 20.0 degrees Celsius. Moles of magnesium used, we're going to get that from the grams directly. We'll need that later. Okay, I'll wait on that. Now, this is very important. Okay, you should understand clearly that you collected some gas on top of the eudiometer, and that was hydrogen. And because we collected by water displacement, we also have some water evaporating. So you have, guess what, a mixture of two gases. When you have a mixture of two gases, you have Dalton's law of partial pressure involved in this problem. So Dalton's law, you have to be able to identify that, just like your take-home quiz. Now, in order to use Dalton's law, we need pressure total, okay, equals the partial pressure of one gas. Okay, I said A there, but I should probably just make that hydrogen. That's what we're trying to collect, dry hydrogen, plus the partial pressure of water. Now you should clearly know, okay, the water is tied to the temperature, right? We're going to need a table to manage that value, okay? Any case, I'm probably going to have to attach that table to show you. Any case, so the temperature of the water bath is 20, and there's the partial pressure of the water there. Okay, so that's attached to each other. So that's how we're going to get the pressure due to that. We know that at different temperatures, there's different amounts of vapor that's produced by the water, different amounts of gas that becomes available as the liquids overcome their intermolecular attractions. Okay, back to the problem. So we have a Dalton's law problem initially to get this dry hydrogen. That's what we're about. We're all about trying to get the partial pressure of hydrogen, because in this lab, I'm trying to figure out I'm trying to see if I can get 22.4 liters per 1 mole, the molar volume. Okay, any case, before I get that, I need the what? Before I can solve for this, I need the total pressure here. So yes, there's a Dalton's law, but there's also a manometer problem, a manometer problem. So there's two scenarios I have to deal with. In order to get to the Dalton's law, okay, which have to be second, I first have to deal with the manometer. I have to deal with what this total pressure is here. Okay, well, very simply, I know the atmospheric pressure pushing down is approximately 764 torr today. Okay, I know that the height of this in water, okay, so you have the height column of water, and let's just say mine was 51.23, and that was millimeters of water, which you should clearly see, H2O. This is not a pressure unit that we use. We use millimeters of mercury. So I'm going to have to convert to millimeters of mercury. So gosh darn it, before I even get to the manometer, I've got to do a height times density equals a height times density. It's an inverse relationship, and very clearly, okay, I'll make this on black. We know the height in the water is what we're trying to find. The density of water is 1. And I'm trying to find the height for, I'm sorry, we know the height in water to be this number. You know, the density is 1. I'm trying to find the height in mercury, and of course, the density of mercury is 13.6 grams per milliliter. So essentially, solving for this unknown, we're solving for this unknown h, we're dividing by 13.6. We're going to make this height 13.6 times smaller. Okay, why? Because mercury is so much more heavier. It takes a heck of a lot less, 13.6 times less, to get its equivalent in pressure and supporting that liquid. So using my calculator, okay, I get 51.23 divided by 13.6, and I get a grand total, and it's not going to be much because this really isn't that high. I get 3.77 torr, or millimeters of mercury. Torricelli, millimeters of mercury, the same thing. So the height in column mercury is 3.77. That's what I get. Okay, well, guess what? My manometer problem is easy. I know that the what? Who's winning? Atmospheric pressure or the pressure in this container? Well, atmospheric pressure is winning by how much? By 3.77. So, we're scrolling this down. The partial pressure in the uniometer is very simple. The manometer problem states that the atmospheric pressure is winning by this much. So that means the gas is losing by this much. Either way, okay, how you want to say it, 764 torr, that's atmospheric pressure that was converted from the millimeters of mercury, the inches of mercury given in class, minus 3.77 torr. So there is my manometer problem. So 764 minus 3.77, and I get 760.23 torr. I'm just going to keep all raw numbers. So my partial pressure is 760.23. It has to be less, okay, than atmospheric pressure. Why? Because I know water is being supported. This atmospheric pressure is not only pushing back this gas, it's supporting this much water. So collective efforts of the weight of the water and the push down by this gas is equal to 760. So if I know this value, what's left is there. How many different ways to think about that? Okay, so partial pressure of H2O in water. Well, it's tied to temperature. I need a table to do this. Okay, give me a second, I'll pull it up. Okay, so I'm back with the vapor pressure ditto that you saw that I taped to the lab table. Any case, here it is. So let's go find our temperature. All right, and my temperature was about 20 degrees Celsius. So I'm going to zoom in on that. So I'm going to guess it's 2.3388. Now, to do like 20.5, it would be 0.5 the difference between here. If you did 20.8, it'd be 0.8 the difference. So if I had 20.8 as my temperature, I would find, subtract these two numbers, whatever that might be. Let's pretend it's 1. I'd take 80% of that, and I would add that to this one. So again, if I had 19.5, I'd find the difference between 19 and 20, which let's pretend is 0.2, then I would take 50% of that number, which would be 1, and I would add that to this. Okay? So I'm going to pretend mine was 20. I get 2.3388, okay, kilopascals. 2.3388. So 2.3388. Probably get it wrong by the time I close all this stuff out. 2.388. Let's get back to where I was. Okay. So 2.388. And let's do that. 2.388, and this is kilopascals, kPas, we would say in my Regents class. And I want to convert that to torr, and that's easy. 101.3 kilopascals, okay, that's 0.3, is equal to 760 torr. Okay, and I'm just going to do that for myself. And for you, of course. Okay, so it's 2.388, okay, times 760, divide by 101.3, and I get myself a number that states about 17.91, and of course that's torr. That's my pressure, 17.91 torr. Of course, now, what did we just do? We just found, okay, the manometer issue. We found the total pressure, okay. Was 760, okay, and I see I made a mistake. This is the total pressure in the manometer. This is equal to PT. Okay, I got to make it, you probably saw it before I did. This is not the pressure of the hydrogen. Okay, the pressure of the hydrogen, because the first part of the problem, sorry if I confused you, I'm going to go slow. The first part of the problem, we needed to find the total pressure. So how did I find that? I did the manometer problem. Okay, I knew that this height in column in mercury was 3.76. I subtracted it, okay, to get the pressure here. So this is the total pressure. Let's highlight that. It's pretty important. Okay, I incorrectly made that the hydrogen. Now, Dalton's law, that's the second thing we're going to do here. The second part of this, okay, is Dalton's law. Now, what we're going to do is we're going to take our Dalton's law, partial total pressure is equal to the partial pressure of my hydrogen, which we're trying to get the dry hydrogen, plus the partial pressure of my water. Well, we just figured out the water through the table to be 17.91 torr. And of course, the total pressure that I did incorrectly is 760.23. What's the partial pressure of the hydrogen? I'm sorry. Well, that's going to be, of course, subtracted. So minus 760.23. So I subtract that, and I get a number. Okay, change the ink because I like to, and I make 742.3 torr. Okay, obviously this pressure plus this pressure equal this pressure. Hey, Dalton's law, that's the second part. So my hydrogen is 742.3 torr. Okay. All right. Now, what do we got here? Fraction of the volume in eudiometer, which is pure H2. Okay, what we're going to do now is that what would be the volume? Okay, what would be the volume, okay, of the H2 if there was no water vapor? Well, as we talked about in class, it would be less. If there was no water vapor, there'd be less pressure, and this would definitely contract a little bit. So we want to find the volume of just a pure hydrogen. Now, the fraction of the volume in the eudiometer. Okay, well, the fraction of the volume, remember the eudiometer is a container, is a fraction of the what? What's proportional in a container? Volume, moles, and, yeah, someone said it, pressure. Volume, moles, and pressure are all proportionate. So what's the fraction of the volume in the eudiometer? Okay? Well, total pressure is 760.23. That's what we got from the manometer part of this problem. And the hydrogen is 742.3. I'm doing basically a volume fraction, which is the same as a mole fraction. So 742.3 divided by 760.23, okay, gives me a mole fraction to be, just change the ink because, well, I can, okay, is going to equal to me 0.9764, carrying a lot of sig figs, don't care here. This has no unit. This is a volume fraction, which, by the way, is now a mole fraction because moles, volume, and pressure. Cool? Okay, you probably don't think so. Okay, but who? I do care. I give a hoot. I don't pollute. Okay, so X is of H2. That's the mole fraction. It's the volume fraction. It's the pressure fraction. Hey! Okay, so volume of H2 collected. Okay, so we're going to now know what the volume of the H2 minus. Well, this is the fraction of the pressure, fraction of the moles, fraction of the volume. So I'm going to take this fraction, 0.9764, and I'm going to times it by the total volume. Okay, what's the total volume? Total volume is what you guys read on the manometer with both gases. So the total volume in my case is 45.03. 45.03. So I multiply my fraction times my total to get just the volume of the dry hydrogen. I'm seeing what the volume would have been if there was no water. And I'm using a volume fraction. Aha. Okay. So I get 43.96 milliliters. Notice it's lower than what I had originally. Okay. So the volume of H2 collected is this. But now I want to correct for STP. Because the whole point of this lab, party people, and pay attention, okay, we're almost getting to the end here. The important part here is that I want to find the volume when there is no, at 1 mole. I'm going to find that molar volume. It'll make more sense when I get to the end, okay, the molar volume. So how do we do that? Well, VP over T equals VP over T. So I want to find the volume. So currently I have 43.96 milliliters. The pressure that this gas is currently under is, okay, in this container that it's subjected to, okay, is going to be, what was the total pressure that I have? Total pressure was 760.23. So it looks like I erased something here. Okay, so the partial pressure is 742.3 for water, but 760.23 is my total pressure. So 760.23, and my temperature was at 20 degrees Celsius. So my friends in chemistry, okay, this becomes 293. Now I want to solve for what? I want to solve for, okay, at STP. So I'm going to get rid of the rest of this, make it solve for STP. Okay, what's the new volume? Okay, when the pressure now is 760, not going to change that much, and the temperature is 273 Kelvin. I'm going to solve for V. Okay, so I get the volume, once I solve this PV over T combined gas law dynamic problem, my volume corrected for STP, for ST conditions, becomes 40.03 975 milliliters. Now my friends in chemistry, that changed. It got smaller by a little bit. Okay? Temperature went down. But what? Pressure stayed pretty constant. Temperature goes down, volume goes down a little bit. Okay. Here comes the molar volume at STP. This is the what we're going to do here now. Okay? Way back when, we have moles of magnesium. I've got 0.067 grams. I want to convert grams to moles for magnesium. I know from the periodic table 24 grams equals 1 mole. And when I do this, I get 0.067 times 24. Actually, no. 0.067 divided by 24, as my equation states, and I get a small number, 0.00279 moles. 0.00279 moles. 0.0, my short-term memory is gone at this height. 0.00279. That's my moles of magnesium. Let's go in. Let's go take a peek at the old equation we dealt with over here. Let's see. It's balanced. 1 magnesium. This is, by the way, magnesium chloride. This is hydrogen. So let's look at the question. So let's balance the equation. Okay, watch. There's 1 chlorine, 2 chlorine. So I'm going to learn to put a 2 here. If we did boxes, you would need 2 here. 2 H's, 2 H's. So for every 1 magnesium, how many hydrogens, if you were to do the boxes and do the law of conservation of mass? For every 1 magnesium, there's 1 hydrogen produced. So if I know the moles of magnesium, don't I know the moles of hydrogen produced? Yes, you do. This is the power in chemistry now that we understand moles. The same moles or number of Mg atoms is the same number of hydrogen particles. So there's the aha. To get moles of H2, you use the moles of magnesium. Now, convert this to liters, 0.040975. That's liters now. I'm going to take that 0.040975 and divide by 0.00279. And I get, okay, again, this is my 14.6 liters per mole. Now, if I used real numbers, my number would come close to 22.4 liters per mole. So I found the liters per those small amount. Let's go find what it would be for 1 mole, just like we divided by what? Many grams in our lab. So by dividing by liters per mole, we should get 22.4. And I bet if you follow along, your number is close to this. It's not perfect because of some experimental and some real gas errors. And then I want you to do a percent error and find the number of hydrogen atoms in the eudiometer tube. So do that for homework.